is a learning curve for me too. But I did want to try to get that done fairly early. So, but you know, I got to bed by 2. That's fine. Which I usually do anyway, so it's not like a big deal. So yeah, if any of that leaves you with other questions, please ask me, talk to each other about it. But overall, I thought you guys did real well. Anything particular you guys want to look at or ask about before we start talking about chapter 4?
I had a real trouble with the problem. I think it was 7, where it was. It's either 7. It was. I think it was 7 and 6. It was the question where it gives you 2 points and it says to figure out an equation, and then the other one was to figure out a purpose. I figured out question 7. That's not a problem. It was number 6. I think is the one I got wrong.
Yeah, number 6 is the 2 points.
I don't think I got that one correct. I'm having a hard time with that one.
I can tell you why if you'd like.
Yeah.
Okay. So you're given f of -3 equals 3 and f at 4 equals 0. So these are the x values and those are the y's, right? So that's the point 4, 0, and this is the point -3, 3. If you look at particularly your scratch paper, you switched that negative.
Yeah, I just saw that.
Yep. That's the only thing that went wrong.
That makes sense.
Which is, again, why the scratch paper is handy, because looking at the answer you have, it's like, where the heck did that come from? But looking at the scratch paper, I can go, oh, okay, that was all. Okay, that happens, and adjust that. One of the things that I did want to mention, so I appreciate you bringing that up. The value depended on what your particular version of the test had, but when you were asked to make a perpendicular, so given this equation and you wanted the perpendicular through a particular point, through, let's say, I want to go through, say, 4, 7. Why not? So lots of you did very appropriately take that -2 and turn it into its opposite reciprocal. So you changed it from a negative to a positive and flipped it for the slope of that perpendicular. But there was a lot of trouble properly coming up with what the new constant was.
Yeah, this was my least favorite question.
Well, we know it's got this slope, right? We know it goes through the point 4, 7. So if we use that point slope form, then y minus the y value equals the slope x minus the x value, and that's the equation of our line. You can distribute that 1/2, add over the 7. So it's just the same type of ways that you would make a line otherwise. All we need is a point and a slope. The issue is we have to essentially ignore the constant, or the, if you want to call it, the y-intercept that we've been given. That +1 has no bearing on the line that we're trying to build. We want to be perpendicular to that line. The only thing we care about is its slope. So we really have to ignore that +1 completely, and that can be hard. We want to do something with it. even if you like making lines the other way, just going directly to the slope-intercept form, the process would be the same. You know the 1/2. We want to figure out what that b is. So plug in the 7, plug in the 4. 7 equals 2 plus b, subtract the 2, subtract the 2. So in either case, we can find that y-intercept, that new y-intercept, but we have to ignore this +1. It has no bearing. It's not even there. It doesn't matter. I can't even see it. Does that make sense? Okay.
Yeah, I'm pretty sure I messed up my algebra when I was solving that.
It was probably one of the most missed questions, not because of the slope. Almost everybody had the right slope. There was just one issue or another with finding that that constant. Excuse me. Anything else you want to look at? Okay, then let's look at chapter 4. So chapter 1 was about just functions in general. So chapter 1 was just about general functions. Chapter 2 was a review of lines or linear functions. Chapter 3 was a review of quadratics. And chapter 4 kind of continues this pattern with lines and quadratics by extending this to general polynomials. So lines are, of course, functions of the form, or that can be expressed in the form ax plus b. Quadratics are of the form ax squared plus bx plus c. Polynomials take this and extend it. Lines are x to the first. Quadratics were x squared. General polynomials can essentially be x to higher and higher powers. There are restrictions, though. It can't be any power. The generality for our polynomials is that we have to have our powers be positive whole numbers. So say x to the 5th plus 4x to the 3rd minus 2x squared plus 1. That's a polynomial. All the x values are nice positive exponents. They're all nice whole numbers. This will be a nice, well-behaved polynomial. Excuse me. None of the x's are being divided, so we don't have anything like minus, say, 4 over x to the 3rd. That would be an x to the -3 if we tried to write it up on top. So that can't happen. We can't have, say, an x to the 2/3, because that would be x squared's cube root, if you remember your fractional exponents, which you'll need to for chapter 5, by the way. So none of those types of things can happen, just nice, positive whole number powers. We'll often see this written out in general, a general polynomial. You'll see it written out in a way that's a little bit Now, it can be a little bit strange at first. Like for here, for lines, often we use M and B just because of the slope. But A, B, and then A, B, C, you can imagine if we went to a third polynomial, a third power polynomial, we could use A, B, C, D. But as soon as we get to be much larger than that, that starts becoming problematic because we start wanting to use letters like, A, B, C, D, E. Well, I don't want to use E because E is special. We could use A, B, C, D, F, but F is kind of special for functions. H and G we use for functions. I certainly don't want to use I. So using more and more letters starts to become problematic. So instead, what we often tend to do is index the letters that we're using. I'll show you what I mean. So we'll have something like, if we had a general polynomial that's x to the fifth, we'd say a5 x to the fifth plus a4 x to the fourth plus a3 x to the third plus a2 x squared plus a1 today x plus a sub 0, a0. You'll often hear me say, and lots of people say, a naught from the Latin for 0, just as a habit. So sometimes you'll hear that as a naught. Trying to let that throw you off. So instead of having A, B, C, D, E, which I don't want to use, F, which I don't want to use, we'll have the constants just use the same A for all our coefficients, but index them, number them, essentially. This is our, our first A, our second A, our third A, our fourth A, and so on. Notice here I've indexed them along with the powers. So it's really clear that A4 is the coefficient for the x to the fourth term. The A2 is labeled nicely to go along with the x squared term. Excuse me. You don't have to index them that way. You could index them with any set of numbers you want, but this is how we kind of standardly index for polynomials. You'll start to see more and more things written out that way as you go along in mathematics. Have you guys seen things written out like that before?
Kind of. I mean, they use sub numbers like that when you're labeling things like resistors and such in electronics.
Yep, absolutely. Now, this is for a general polynomial with an x to the fifth. When you try to go a little further and write out what a completely general polynomial looks like, it can look even a little bit more strange. So if we wanted to do a completely general polynomial where this power of the x, this 5, could be anything, we've got to label it as x to the n for any n power. That would make the coefficient, we'd label it an. But then the next one would be, well, 1 less than whatever that n was, x to the n minus 1 power. So this is really the same as the x to the fifth and x to the fourth. It's just, since we don't know what that highest power is, it's being labeled as an n. So it can look a little bit more intimidating, but it really is just this power and then less by 1, less by 1, less by 1. It just looks like there's a lot going on. N minus 2.
I'm trying to orient myself through this, and I have a few questions.
Shoot.
Number one, if your x, your p of x, your x, is that the same value that would be in all of those x's?
Yes, absolutely.
Okay, and then your third p of x is a capital P versus a lowercase p. What does that indicate?
I just wanted to make a distinction between this one being the specific fifth one. And I still wanted to use P for polynomial, but I wanted to make it different. So I made it capital.
And if you wanted to have different values, you would have different letters instead of X. So if you had A5 X to the fifth and A4 Y to the fourth, you would just have different.
They'd have to be different letters there. And if I wanted those all to be inputs, this would have to be a multivariable function, PXY. So I'd have to have the variables for the inputs to have different things to put in it.
And are we going to see that?
We don't want to go there.
Because doesn't the A represent the coefficient?
Yeah, those A's are just constants. So they can be whatever they happen to be for the particular problem. Like here, A5 is a 1, A3 is a 4, A2 is a -2. A1, there's no A1 here because there's no X to the first. So A1 is a 0. And then A0 is a +1. But the X is the variable in question here. So just like here, if I asked you to evaluate G at 7, you'd put the 7 in for both of those X's, right? I'm gonna say yes. Put that 7 in for both of those X's. So down here, if you wanted to find this small p at 3, you'd put a 3 in for every one of those X's. Same thing down here. You're right, though, Crystal. If we did have multiple input variables, they'd have to be, X and Y. We could even index the X's, X1, X2, X3, but that would be start to get crazy notation-wise. But that does become a multi-variable function. We don't mess with those until Calc 4. So that starts to get really fun, but starts to become a lot.
Thank God I'll never make it that far.
No. So this pattern will continue. Like if this was a X to the 10th, you can imagine we'll have a lot of terms. If it's X to the 45, there'll be a lot of terms. So this pattern of reducing the power by 1 will continue on, hence the ... until it eventually gets down to the A2 X squared, A1 X to the first plus A sub 0. So in general, we don't know how long it'll be, so we give it the space to be as long as it's going to be. So oftentimes, particularly this n, n-1, n-2 could make people think there's a lot more going on. This just says that the powers will go down by 1, the powers will go down by 1 until they reach X to the first. And technically, there is a little X to the 0 down here because X to the 0 is just 1. So some people like to think about that X to the 0 being there because it is. So why not?
So would A be the same number in each one of those different
No,
terms?
and that's why they're indexed. If we just wrote A, X to the 5th, A, X to the 4th, A, X to the 3rd, if they were all just A's, then they would have to be the same.
Oh, okay, yeah. All right.
Yeah, the purpose of indexing them is to say that they are different, is to distinguish them from each other. So let's look at a fairly good sized example here. Let's say we've got 4x to the 6th plus 2x to the 4th minus 5x squared plus 7. So that is of this form. The n is 6. That's our biggest power. Now the x to the 5th that would be there, we don't see the x to the 5th. Well, the reason we don't see that x to the 5th is because its coefficient is clearly 0. So we could imagine, and really should be imagining, that there is a 0x to the 5th in there. And then 2x to the 4th. Similarly, there is a 0x to the 3rd in there. 5x squared. Then there's a 0x to the 1st. And then our constant. So we really do want to start, because it's going to be important later, we really do want to kind of think about, hey, those other pieces are in there. We're just not seeing them or not writing them because there's zeros. There will be times where we will want to write those out. Does that seem reasonable? All right. There is some common language we want to make sure we associate with our polynomials. So some vocab. Polynomials have a degree. The degree of the general polynomial is this highest power of any of the variables. So this n is our degree. So here the 5 is the highest of any powers. This is written, all of these so far are written in standard form. So the highest power is the first one way on the left. So this would be a 5th degree polynomial. This has a highest power of 5. It's also a 5th degree polynomial. Highest power of 6, this would be a 6th degree polynomial. So the degree is the highest power of the variable, I should say. They don't have to be x's, these could be t's. So if we had a function, let's go ahead and use t, g of t equals, say, 5t to the 3rd minus 6t to the 4th plus 7. What is the degree of that polynomial?
4.
Yeah, 4, the highest. Oops, the highest power of that variable. So it's a 4th degree polynomial. As we start going into our next section, that'll be an important distinction, because essentially every 4th degree polynomial behaves in a similar way. Every 5th degree polynomial behaves a little bit differently than the 4th, but all the 5th degree polynomials behave in a similar way. All the 6th degree polynomials behave in a similar way. So really the degree of the polynomial defines a lot of its behavior. Let's see, each term in the polynomial, each term has its own degree. So this is the degree of the polynomial because it is the largest degree, but this is a 4th degree term, a 3rd degree term, a 2nd degree term, a 1st degree term. We could call this a 0th degree term, but we don't tend to. We just generally call it the constant term. So for this, oh, I didn't put my x down here, f of x. So for this example down here, we've got a 6th degree term. This 2x to the 4th is our 4th degree term. This negative 5x squared, the negative has to come with it. The negative 5x squared is our 2nd degree term, and so on. So the degree of the polynomial is essentially the highest degree of any term in there. Being able to reference the terms that way is very handy, because we can then, let's see, I'm gonna make myself some space up here. It makes it easier to reference different things that we're doing. So if we grab another one here, say 5x squared plus 2x to the 3rd minus 4x to the 4th plus 7x plus 1. Why not? We could ask what the degree of the polynomial is. The degree of the polynomial is certainly the 4th degree polynomial because that's the highest power. But being able to reference things like what is the coefficient of the 3rd degree term? Well, the 3rd degree term is this x to the 3rd term. The coefficient of the 3rd degree term is positive 2. The coefficient of the 2nd degree term, 5. Coefficient of you could even ask, well, the coefficient of the 4th degree term is negative 4. Constant term is 1. Coefficient of the x to the 1st term, so the coefficient of the 1st degree term, 7. So being able to reference the terms by their degree is handy. By the way, you will often hear the 1st degree term referred to as the linear term, because x to the 1st is lines. So even if it's not a line, you'll often hear that x to the 1st term be referred to as the linear term, just because that language is stuck and been around for a long time. The x squared, I've heard a couple people say the quadratic term every once in a while, but it's very rare, and we don't tend to. We just say the 2nd degree term or the squared term. But if you ever hear somebody else say it every once in a while, linear term, that's just the x out of the 1st term. So each term has its degree, the power of that term. We have the lead term. We'll often refer to the lead term because the lead term is important in behavior. So the lead term, you want to think of the word lead here, not as the one in front. You want to be thinking of that lead as the one in charge. It's the one that's going to govern the overall behavior of the polynomial. As I said, polynomials of the same degree all behave in a similar fashion. So if we can identify the lead term, then we can identify a lot about how the general behavior of the polynomial is going to be, or what it's going to be. So the lead term, though, should seem reasonable that lead term is the term where the polynomial's degree comes from. So, the degree of the polynomial came from the highest power, or the highest power of any term. That term is the term that's going to govern its overall behavior. So for this f of x, the lead term is the 4x to the 6th. It's the one out in front because we put them in descending order. But over here in g of t, the lead term is that negative 6 t to the 4th. Do include that negative. So the fact that it's t to the 4th will tell us how it behaves. The fact that the lead coefficient is negative, that is the coefficient of the lead term, the fact that that lead coefficient is negative tells us how that is going to be modified. So the lead term is simply the highest degree term.
So when we're working these, do you recommend that we put them in order of like the degree of the terms?
I do. In general, we'll write things in what is called standard form, descending powers, but it's not uncommon to be given a polynomial in whatever order somebody wanted. So it's important that when we're trying to determine what the degree is and what those lead terms and lead coefficients are, it's important for us to make sure we're looking for which one's the highest in case somebody's trying to trick us. Like, I would never try to trick you that way, right? But you're certainly correct that most people, when they're handed a polynomial, will go, okay, I just want to have it be in standard form. So they'll write it in those descending powers. it is a very reasonable and somewhat helpful habit to be in. So, but it would bug me a little bit with this one because I don't like having negatives out in front. They kind of dangle and they sometimes fall off. You lose them pretty easy. But if you wanted to, you could write this in reverse standard form and nobody would give you too much trouble. I mean, nobody would get mad at you, I don't think. Minus helps that negative stay more secure, locked in there, and still makes it easy to tell which one's the highest and which one's the lowest. So having them be organized is really helpful, but we don't want to assume, you know, when you look at a general problem, you just kind of want to make sure, hey, did anybody slip in a higher degree term in there and not tell me? Does that make sense, Andrew? So most of this vocabulary is really just so we can refer to things. It was actually hard to write this out before and talk about these things and never say the word degree. You know, I kept saying, you know, the highest power or the power. I wanted to say the degree. I wanted to say the lead term. So, you know, for me, yay, I get to now use that vocabulary. But for you guys too, when you're referring to things and when things are being pointed out, having a nice vocabulary for those big things we're going to look at is going to be really helpful.
I've heard it before. I don't remember exactly where though.
You will have. I mean, even when you took things like 65 and 95 and you dealt with quadratics, because a quadratic is a polynomial. A quadratic is just a second degree polynomial. So we often hear that language kind of sprinkled through some of our other things. A lot of times, even if that language isn't formally introduced, it's the language that you know we talk in. So it's hard to avoid using things, the words like degree. So oftentimes people pick up a fair amount of this language as they go along, but we want to formalize it.
I think in Math 65, Miss George had us some questions where he had to figure out what the degree of the polynomial was.
Not unusual to have heard a fair amount of this vocabulary as you went along. Can you guys see all those little dots and squares when I do that?
Yes.
Yeah, cool. Just curious.
Looks kind of neat.
It is. I'm actually playing around with a different program for, instead of this whiteboard. I might start using it next week. It gives me a little bit more control, so we'll see. Let's see. Generally, when we deal with polynomials, one of the reasons we like polynomials, we as in, you know, anybody who does any kind of mathy stuff, physics, sociology, if you model anything, you generally try to use polynomials if it's appropriate. And the reason for that is that polynomials are very well behaved. They are nice and smooth and continuous. They don't have breaks or cuts in them. They don't have what's called discontinuities. That's spots where they break or have asymptotes in it. They don't have, when they turn smoothly. They don't have sharp, jagged corners in them. They are nice, well-behaved functions. When you do go on to play around with some calculus, Crystal, or any of you, polynomials are your favorite. Polynomials are everybody's friend because they don't do anything weird. They don't have discontinuities. You don't have to use any special tools. They are just the nicest functions to work with, which is why we tend to use them to model different things. We've played with some of the language for how the function is behaving for a polynomial because we talked about it in general. But just like the functions before, we can ask, hey, when is this function increasing? And the function increases when the y values go up as we travel from the negative x's towards the positive x's. So as the x's increase, where do the y values increase versus where do the y values decrease? So it's going to increase for that part of the graph. It's going to increase over this part of the graph. And it's going to be increasing on this part of the graph. So, and I know you guys have done this, a little bit of this before. So it's going to, these x values are going to cause it to increase. These x values are causing it to increase. And these x values are causing it to increase. So if we're asked where we're increasing, I'm going to label those A, B, C, and D. We'd be increasing from negative infinity to A, unioned with, it's the, kind of the way to say and in intervals. So this interval and the interval from B to C, unioned with the interval from D to positive infinity. We're decreasing almost everywhere we're not increasing. So we'd be decreasing on that part of the graph and that part of the graph. So these x values are causing our function to decrease. These x values are causing our function to decrease. So we're decreasing on the interval from A to B and on the interval from C to D. And we've talked about that increasing and decreasing language a little bit before. Do notice that the increasing and decreasing, the intervals of increasing and decreasing are x values. I've always kind of tried to note when you're asked where is the function increasing, there's a lot of hidden things in that question. It really is for what x values are the function values increasing. We tend to just say, where is the function increasing? But that where, as we talked about before, that where is input values, is the function increasing. So function values increasing, function values are the y values. So what x values make the y values go up? What x values make the y values go down? That seem reasonable? Got my cute cup today. I said that it's decreasing almost everywhere it's not increasing. The only place it's not is these points where they meet. Notice with the parentheses, that A is not included because of the round parenthesis, that A is not included in the increasing and that A is not included in the decreasing. That point at A, we are neither going up anymore, nor have we started to go down yet. It's that kind of point in between. And those points collectively are referred to as extrema. Derived from the Latin for root that's for extreme, but is extrema. Extrema, they're called extrema because they are our relative maxes and mins. This first point up here is certainly not the highest point anywhere on the graph. The graph does go higher over here, so it's not a global extreme. It's not the highest point anywhere on the graph, but it is a local extreme. It is the maximum value in this local area. This is a minimum in its local area. So it is a relative minimum, sometimes just called a local minimum. This point as well is a local extreme. It's a local maximum, highest in its little local area. None of these are global extrema. So our extrema can be relative, or again, local if you prefer, maximums. They can be relative minimums, and they can be global maxes and mins, often referred to as absolute max and absolute minimums. So our extrema contains all of those. So when you're asked, you could be asked, find the absolute maximum, find the relative minimum. You could be asked them separately. But if you're ever asked to find the extrema, you're finding all relative and absolute, all local and global mins and maxes. So extrema covers all of them. So we have a relative max at A. So a relative max at A. The relative max, you'd want to give the X value and the Y value. So we'd have to either be able to look on the graph and see what that Y value is, or have the function to plug it into. And we have a relative max at C and whatever C's output value is. We have a relative min at B and F at B. We don't have any absolute mins or maxes because this is going to go down and down forever and up forever. We don't want to say it has an absolute max at infinity because infinity isn't a number. Infinity is a concept. So to say something has an absolute maximum, we have to be able to give that maximum a value. And we can't give it a value here, so it just has no absolute max, no absolute min. So I'm just going to say none. So if asked what the extrema were here, we'd just be giving those 3 points. You generally should label them. You're often usually asked to label them. So the relative maxes, label relative max, the relative mins, label relative mins. So again, you've probably played with those ideas before. Yes? We're just kind of trying to formalize that language a bit. Particularly, I have found, if I give a question and say, hey, find the maximums, people will go, oh, okay, there are the maximums. Ask for relative maximums, people get a little bit more unsure. But if you just say, hey, label all extrema, that often kind of freezes people a bit. So getting comfortable with that language of extrema being just all of these types of pieces, getting used to that language is helpful. Andrew.
So why didn't we include point D in the relative minimums?
We do.
Oh, gotcha.
I was waiting for somebody to yell at me.
Write it down, so I was curious.
Yep. That point D is another relative min. So really, anytime we switch from decreasing to increasing or increasing to decreasing, every one of these boundary points should have an extrema in it. So when we go this A to A should have an extrema, that B to B should have an extrema, the C to C should have an extrema, and the D to D should have an extrema. Fair? Now, when you stop having polynomials, that stops being true. It's one of the reasons we like polynomials, is because we know nothing weird is going to happen. You're not going to have some asymptote occurring at A. The graph's not going to do anything crazy at A. It's not going to have holes or gaps or jumps or anything, because polynomials are actually often referred to as a well-behaved function. It means it is continuous and smooth. Actually, the technical term for smooth is a differentiable, but sure, play with that in calculus. Crystal. You guys all plan on taking calculus, right? Except maybe Crystal. And I'll see if I can talk her into it over time.
I got to get through trig first.
And trig is fun.
I don't even know how high I have to go in math because I'm going for engineering, mechanical engineering. So.
Calc 4.
Yeah,
and
so
then you'll take differential equations and linear algebra And man, your fractions will be so rock solid by then. It'll be awesome.
I hate fractions.
Give it time.
Yeah,
Never mind.
I'm taking
Go
a
ahead.
lot of math also.
This is the highest I have to go. Woohoo!
Yeah.
Embedded systems engineering,
So
so
far.
all of it basically.
I have a morbid curiosity about trig, so we'll see.
How about you, Aaron?
I have one more, so trig.
Trig? Okay.
I don't know why I put myself through this kind of abuse.
Because the payoff is there.
Well, I used to work with nuclear reactors when I was in the service.
Right.
So-
I remember you mentioned that.
I used to do really high level math all the time, and then I just sort of forgot about it all.
Yeah. The nice thing is that perspective will pay off a lot. In, small ways here and there, and in big ways here and there. So one of the things, I got to let you guys head off, but one of the things you're going to see in your reading and want to play with and ask any questions that come up from it is about functions that are even and odd. And I want to kind of leave you with a note about even and odd. The key about an even function is that it is symmetrical about our y-axis, up to my ability to draw it. I'm doing so well. Up to my ability to draw it. So an even function, everything on this side, everything on the positive side is mirrored over to the negative side. So the function at any x value is going to be equal to the function of the opposite x value. So say f at 3 is the same as f at -3. F at 10 is the same as f at -10. So you get that mirror symmetry, often called y-axis symmetry, because it's flipped around that y-axis. It's not common for functions to be even. A lot of functions are even, but the kind of generic function isn't even. Like this function's not even close to even. If we flipped it across that y-axis, it wouldn't land on itself. So not even. But lots of things are even, and when they are, we like to take advantage of that, because everything we find out over here, we get for free on the other side. So that's an even function. Odd functions, by contrast, the one side of the function, it is mirrored, but it's mirrored in reverse. So an odd function, everything that's going on the positive side is mirrored to the other side, so is kind of the same as the function on the other side, but the signs oscillate. So if this was 2, so the function evaluated at 2 is going to be the same as the function evaluated at -2, but it's going to change from negative to positive. Or from positive, same answer, but changing from positive to negative. So both even and odd are about symmetry. Even has y-axis symmetry. We often look at the odd function as kind of rotating. So this piece rotates down here. Because of that, this is often called origin symmetry, or odd symmetry. This is often called y-axis symmetry, or even symmetry.
That's like an x cubed equation, right?
Yeah, an x to the, well, a some x to the third. If it's just plain x to the third, yeah, x to the third has a nice origin symmetry. If you have some x to the thirds, will behave very nicely. But you can have some x to the third equations that, that don't. That's not even, that's not odd. And the even and odd do come from degrees of polynomials. So read through that section, play with the material on it. Ask any questions that come up from it. The book tends to handle it very well, but that's the really short version of even and odd. We can talk about it more if you guys need to. Okay. Anything else before you guys head out today? Okay. Well then, go forth and play with it and have a wonderful day.
Thank you.
You're very welcome.
Thank you. Have a good day.
You too.
Thank you, Matt.
Mm-hmm.